In the last lecture, I have introduced the problem of statistical inference. In the problem of statistical inference, we try to convey something about the parameters of a population, parameters of a statistical population. So, our model is the following. So, we consider for example, x is a random variable with probability distribution, say p theta, where theta belongs to a parameter space script theta, and x 1, x 2, x n is a random sample from this population. I have told that we can consider the problem of making inference on certain parametric function of theta, that is g theta. I told that there are three types of major ways in which we can make the inference. One is the problem of specifying a value for the unknown parametric function. We call it the problem of point estimation, and in the previous class we have discussed the criteria for judging the goodness of a good point estimator and also the methods for finding out the point estimator. Many times it is desirable not only to specify a single value, but rather a interval of values for the parameter. For example, we say that the expected amount of rainfall during this monsoon will be say 150 centimeter to 170 centimeters. Rather than specifying a value saying it could be 160 centimeters, we may say 150 centimeter to 170 centimeters. We may say that the average growth rate of the economy will be between 6.5 to 7%, rather than saying it will be 6.75% or 6.8%. We may give an interval. This is called the problem of interval estimation. Now, in statistics we handle the problem of interval estimation by associating a probability statement with that is called confidence interval. So, let me introduce the confidence interval. Confidence interval. So, let us consider t 1 x and t 2 x. So, here x is denoting x 1, x 2, x n, the random sample. So, t 1 x and t 2 x be two statistics such that probability of t 1 x less than or equal to say g theta less than or equal to t 2 x is equal to 1 minus alpha for all theta belonging to theta. Then t 1 x to t 2 x is said to be 101 minus alpha percent confidence interval for g theta when x is equal to x is observed. That is this is a sample. Then on the basis of that I calculate t 1 x and t 2 x, and we say this is 101 minus alpha percent confidence interval for g theta. Now, naturally the problem of finding out the confidence interval reduces to the problem of finding out shortest length confidence interval with a given confidence coefficient, or so this 1 minus alpha is called confidence coefficient. That means, given 1 minus alpha, we should find out t 1 t 2 such that t 2 minus t 1 is the shortest length. On the other hand, if we fix the length, we should try to find out that t 1 t 2 for which fixed t 1 fixed distance t 2 minus t 1 1 minus alpha is the maximum. So, the problem is that shortest length fixed shortest length with fixed confidence coefficient, or fixed length and highest confidence coefficient. Now, the problem cannot be solved by finding both the things simultaneously. What we do? We try to find out the shortest length intervals for the fixed confidence coefficient. Now, this problem of finding out the shortest length confidence interval is closely associated to the problem of finding out the most powerful tests in the testing of hypothesis. In this particular lecture, I will introduce the method of pivoting, where we use a function of the sufficient statistics to derive the confidence intervals, and they turn out to be later on that they are actually the best confidence intervals for those situations. So, let us consider say confidence intervals for parameters of a normal population. So, we have say x 1, x 2, x n, a random sample from say normal mu sigma square distribution. So, we want to find out confidence interval for say mu, for the mean mu. I will consider two different cases. First case is that the variance sigma square is known. In the case when the variance sigma square is known, we may consider the sufficient statistic x bar, and the sufficient statistic x bar follows normal mu sigma square by n. Therefore, x bar minus mu by sigma by root n, this follows normal 0 1. So, I am actually using the method of pivoting. What we have done, I have considered the sufficient statistics. Based on the sufficient statistics, I have considered a quantity which is having a distribution free from the parameters, and this quantity which I call pivoting quantity, it is having the variable as well as the parameter for which we need the confidence interval. So, if we consider the standard normal distribution, in the standard normal distribution, if I consider say the point z alpha by 2 and minus z alpha by 2, then this probability is 1 minus alpha. If this is z and this is phi z, the standard normal PDF, then the probability that, let me call it z, then probability that minus z alpha by 2 less than or equal to z less than or equal to z alpha by 2 is equal to 1 minus alpha. Now, this statement we can simplify. This is equivalent to minus z alpha by 2 less than or equal to root n x bar minus mu by sigma less than or equal to z alpha by 2, that is equal to 1 minus alpha, which is equivalent to saying that we can consider minus sigma by root n z alpha by 2 less than or equal to x bar minus mu less than or equal to sigma by root n z alpha by 2 is equal to 1 minus alpha. X bar minus sigma by root n z alpha by 2 less than or equal to mu less than or equal to x bar plus sigma by root n z alpha by 2 is equal to 1 minus alpha. If we compare this with the definition of the confidence interval that I introduced, here if I take T 1 x as x bar minus sigma by root n z alpha by 2 and T 2 x as x bar plus sigma by root n z alpha by 2, then this gives us a confidence interval for the parameter mu. So, x bar minus sigma by root n z alpha by 2 to x bar plus sigma by root n z alpha by 2. This is now 101 minus alpha % confidence interval for mu. Naturally, here sigma is known, but when sigma is unknown, then we cannot utilize this as the confidence interval. So, let us consider that case now. Let us consider the case when sigma square is unknown. When sigma square is unknown, then x bar and s square, sorry, this is x bar and s square are the sufficient statistic. So, we should use them for deriving the confidence interval. So, let us consider now x bar following normal mu sigma square by n, and also we observe that n minus 1 s square by sigma square follows chi square n minus 1, and also we note that x bar and s square are independently distributed. Here s square is actually the sample variance 1 by n minus 1 sigma x I minus x bar whole square. So, we consider root n x bar minus mu by sigma, that is a standard normal variable, divided by square root of n minus 1 s square by sigma square into n minus 1, that is equal to root n x bar minus mu by s. This follows t distribution on n minus 1 degrees of freedom. Note here that this quantity, it is dependent upon the sufficient statistics x bar and s, and it is having the pivot the parameter for which we need the confidence interval mu. So, this can be treated as a pivot quantity, let me call it t. Now, again notice here that the distribution of t is also symmetric about 0. This is t, this is the density function of t. So, if I consider the point t alpha by 2 n minus 1 and minus t alpha by 2 n minus 1, then this probability in the intermediate region, it is equal to 1 minus alpha. So, we can consider the statement probability of minus t alpha by 2 n minus 1 less than or equal to t less than or equal to t alpha by 2 n minus 1, it is equal to 1 minus alpha. So, this statement we can simplify. This value of t root n x bar minus mu by s less than or equal to t alpha by 2 n minus 1, this is equal to 1 minus alpha. This is equivalent to probability of minus s by root n t alpha by 2 n minus 1 less than or equal to x bar minus mu less than or equal to s by root n t alpha by 2 n minus 1, that is equal to 1 minus alpha, which is equivalent to x bar minus s by root n t alpha by 2 n minus 1 less than or equal to mu less than or equal to x bar plus s by root n t alpha by 2 n minus 1. So, x bar minus s by root n t alpha by 2 n minus 1 to x bar plus s by root n t alpha by 2 n minus 1. This is 101 minus alpha % confidence interval for mu. Note here the similarity with the known sigma case. In the known sigma case, the confidence interval was x bar minus sigma by root n z alpha by 2 to x bar plus sigma by root n z alpha by 2. In the unknown case, if you look at sigma has been replaced by s and z value has been replaced by the corresponding t value on n minus 1 degrees of freedom. Of course, when n is large, then z and t value will be almost the same, and also s converges to sigma in almost surely, or you can say with probability, then these two values will also be almost same. Let us consider confidence interval for sigma square. Now, in order to find out the confidence interval for sigma square, again we may have two cases. Mu is known. Now, if mu is known in the normal mu sigma square distribution, in that case the sufficient statistic turns out to be sigma x I minus mu square. So, we may consider here sigma x I minus mu square by sigma square that follows chi square distribution on n degrees of freedom. Let me denote it by say W 1. If you note the chi square distribution, it is a positively skewed distribution. However, so in fact, we need to take two values, one value say chi square say 1 minus alpha 1 and say chi square alpha 2, such that this value should be equal to 1 minus alpha. However, for convenience we generally take this value as alpha by 2 and this value as 1 minus alpha by 2. So, we take it this as chi square alpha by 2 and this value as chi square 1 minus alpha by 2. In that case, this probability will become equal to 1 minus alpha. So, this is only a compromise solution. One may actually get separate different solutions for the confidence interval with the same confidence level here. This is different from the case of confidence interval for mu, where because of the symmetry the confidence interval that we obtained is actually the shortest length confidence interval, but here we may have some variations, but for convenience we take alpha by 2 and 1 minus alpha by 2 as the 2 points here. So, consider the statement and now again we simplify this. This statement is equivalent to chi square 1 minus alpha by 2 less than or equal to sigma x I minus mu square by sigma square less than or equal to chi square alpha by 2 is equal to 1 minus alpha. And this statement is then equivalent to, we take the reciprocal and then consider multiplication by sigma x I minus mu square. So, we get sigma x I minus mu whole square divided by chi square alpha by 2 less than or equal to sigma square less than or equal to sigma x I minus mu square by chi square 1 minus alpha by 2 is equal to 1 minus alpha. So, here we get sigma x I minus mu square by chi square alpha by 2 to sigma x I minus mu square by chi square 1 minus alpha by 2 as the 101 minus alpha percent confidence interval for sigma square. Now, here mu was assumed to be known. When mu is unknown, then we cannot utilize this. So, let us consider the case when mu is unknown. when mu is unknown, then n minus 1 s square by sigma square follows, chi square n minus 1 can be used, and let us write it as W 2. So, probability of, once again we see, now we will be considering the points of chi square alpha by 2 n minus 1 and chi square 1 minus alpha by 2 n minus 1. So, probability of chi square 1 minus alpha by 2 n minus 1 less than or equal to W 2 less than or equal to chi square alpha by 2 n minus 1, this is equal to 1 minus alpha. As before, if we simplify, we get the statement as n minus 1 s square by chi square alpha by 2 n minus 1 less than or equal to sigma square less than or equal to n minus 1 s square by chi square 1 minus alpha by 2 n minus 1, that is equal to 1 minus alpha. So, the confidence interval turns out to be n minus 1 s square by chi square alpha by 2 n minus 1 to n minus 1 s square by chi square 1 minus alpha by 2 n minus 1. For sigma square when mu is unknown. Now, we also notice that if we want to write from here, we can write down a statement for sigma also here. If we take the square root here on, because all the quantities are non-negative, therefore, we may also write a statement like, so if we consider square root of sigma x I minus mu square by chi square alpha by 2 to sigma x I minus mu square by chi square 1 minus alpha by 2, and this is n. So, this is then confidence interval for sigma. In a similar way, here if I take the square root, I will get square root n minus 1 s square by chi square alpha by 2 n minus 1 to root n minus 1 s square by chi square 1 minus alpha by 2 n minus 1. So, this will be again 101 minus alpha % confidence interval for sigma. Let me also give you one large sample formula for the variance here. We may consider the asymptotic distribution of chi square is also normal. So, in case we are getting the value n to be quite large, then we may approximate root of 2 n into chi square minus I am sorry, let us not take this one now, let us take the examples for this. So, a new vehicle has been designed and the metal part of the front portion, the braking strength of that has to be checked. So, braking strength in of the front part, a new vehicle is normally distributed in 10 trials. The braking strengths were found to be say 578, 572, 570, 568, 572, 570, 570, 572, 596 and 584. we want a say 95% confidence interval for mu say. So, here the unknown variance formula has to be applied. So, we will consider x bar plus minus s by root n t alpha by 2 on 9 degrees of freedom. So, if we calculate here x bar turns out to be 575.2, here n is 10 and s turns out to be 8.7024. So, we look at the value of t on alpha by 2, that is 0.025 on 9 degrees of freedom. From the tables of t distribution, this value is found to be 2.262. So, we calculate x bar minus s by root n t alpha by 2 9, that value turns out to be 568.9751 and x bar plus s by root n t alpha by 2 9, that turns out to be 581.4249. So, here in this particular problem 568.9751 to 581.4249 is 95% confidence interval for mu. A random sample of say 100 items gave a sample standard deviation, that is S is equal to 0.01 millimeters, and we want say 95% confidence interval for sigma. Now, we can apply the formula for the unknown mu case. The formula for the standard deviations confidence interval is square root n minus 1 s square by chi square alpha by 2 99 here, and similarly this value here. So, we calculate this here. Here the value of s is 0.01 and we calculate chi square 0.02599 from the tables. This value is approximately 129.561 and chi square 0.975, that is 1 minus alpha by 2 on 99 degrees of freedom, that is approximately 74.2219, and here n is equal to 100. So, square root 99 s square divided by 129.561, that turns out to be 0.00874. Similarly, root 99 s square by 74.2219, this turns out to be approximately 0.01155. So, 0.00874 to 0.01155 is 95% confidence interval for sigma here. Let us consider another problem here. X bar, here x i's are the measurement errors and the precision in measuring the errors turns out to be 1 here, and a random sample of 9 observations gives us x bar is equal to 1. We want the confidence interval for mu. Let us consider here. So, the confidence interval will be x bar minus sigma by root n z alpha by 2 x bar plus sigma by root n z alpha by 2. Suppose we want to consider say alpha is equal to 0.1, then alpha by 2 is equal to 0.05. So, z 0.05 is equal to 1.645. So, this value turns out to be 1 minus 1 by 3 1.645 to 1 plus 1 by 3 into 1.645. So, this can be easily evaluated. We get the value as equal to 1 minus that is equal to 0.452 to 1.548. So, this is 90% confidence interval for mu. Here I have assumed the sigma to be known. Let us take one more example here. X 1, x 2, x n denote the weights of certain packed food, and for 10 items the weights were taken, and then it turns out that the sum of the weights is equal to 159 and sum of squares of the weight is equal to 2531. We want the confidence interval for say mu, and we want say 90% confidence interval for mu. So, here n is equal to 10. So, we need to look at the value of t at 0.059. Now, this value from the tables of the t distribution turns out to be 1.833. Now, from the given data x bar can be calculated, it will turn out to be 15.9, and the value of s, that is square root 1 by n minus 1 sigma x I minus x bar whole square, that is equal to 1 by n minus 1 sigma x I square minus n x bar square, that can be calculated to be equal to 0.5676. So, we get the confidence interval x bar minus s by root n t 0.059. This lower limit turns out to be 15.57 and x bar plus s by root n t 0.059 turns out to be 16.23. So, 15.57 to 16.23 is 90% confidence interval for mu. Now, there may be situations where we will have to find out the confidence interval regarding the difference between two populations. So, we consider now two sample problem. Two normal populations. Now, we consider that there are two normal populations, a normal mu 1 sigma 1 square and normal mu 2 sigma 2 square. We want to make certain inference on say mu 1 minus mu 2 or sigma 1 square by sigma 2 square, etcetera. So, we consider random samples from these populations. Let us consider say x 1, x 2, x m to be a random sample from normal mu 1 sigma 1 square, and similarly let y 1, y 2, y n be a random sample from normal mu 2 sigma 2 square. And we assume that the two samples are taken independently. Now, if we want to compare the means, we can consider the confidence intervals for mu 1 minus mu 2. Now, then there can be several cases. The first case is that sigma 1 square and sigma 2 square are unknown, are known. When sigma 1 square and sigma 2 square are known, then the sufficient statistic is only x bar y bar, and therefore, we can consider here based on that itself. So, we can consider x bar following normal mu 1 sigma 1 square by m and y bar following normal mu 2 sigma 2 square by n. So, if we consider x bar minus y bar, then that follows normal mu 1 minus mu 2 sigma 1 square by m plus sigma 2 square by n. So, we can consider x bar minus y bar. Let me denote this difference by eta minus eta, and then we denote this by tau square, then we get divided by tau follows normal 0 1. Note this quantity here, the denominator is known. So, these are the sufficient statistics, and eta is the parameter for which we need the confidence interval. So, we can write down the statement once again from the standard normal distribution here, which is symmetric about the point 0. So, we consider minus z alpha by 2 to plus z alpha by 2, this probability is 1 minus alpha. So, we can write down the statement probability of minus z alpha by 2 less than or equal to x bar minus y bar minus eta by tau less than or equal to z alpha by 2 less than or equal to, sorry, this is equal to 1 minus alpha. So, this is equivalent to x bar minus y bar minus tau z alpha by 2 less than or equal to eta less than or equal to x bar minus y bar plus tau z alpha by 2. The probability of this is equal to 1 minus alpha. So, we can say x bar minus y bar minus square root of sigma 1 square by m plus sigma 2 square by n into z alpha by 2 x bar minus y bar plus square root of sigma 1 square by m plus sigma 2 square by n z alpha by 2. This is 100 1 minus alpha percent confidence interval for mu 1 minus mu 2, in this case when the variances are known. Now, when the variances are not known, then we cannot use this formula. In that case, we consider some special case. Sigma 1 square is equal to sigma 2 square is equal to sigma square, but this is unknown. If this is unknown, then we consider first of all x bar, y bar, s 1 square and s 2 square. If we consider, then they are all independently distributed. The sufficient statistics x bar, y bar, and then of course, this one will get combined, but I write it like this itself. So, you consider here x bar as the mean of the first sample, y bar as the mean of the second sample, s 1 square is the sample variance of the first sample, and s 2 square as the sample mean of the second sample. Now, we apply the distribution theory of these quantities here. X bar follows normal mu 1 sigma square by m, y bar follows normal mu to sigma square by n. So, if I consider the difference x bar minus y bar follows normal mu 1 minus mu 2, that we are writing as eta sigma square 1 by m plus 1 by n. So, this of course, we can write as m plus n by m n. So, x bar minus y bar minus eta divided by sigma root m n by m plus n, this follows a standard normal distribution. Similarly, if we consider m minus 1 s 1 square by sigma square, that follows chi square distribution on m minus 1 degrees of freedom, and n minus 1 s 2 square by sigma square follows chi square distribution on n minus 1 degrees of freedom. Once again, these are independent, because this is based on the first sample and this is based on the second sample, and the two samples have been taken independently. So, by the additive property of the chi square distribution, we can conclude that m minus 1 s 1 square plus n minus 1 s 2 square by sigma square follows chi square distribution on m plus n minus 2 degrees of freedom. We define s p square as m minus 1 s 1 square plus n minus 1 s 2 square by m plus n minus 2. This is the pooled sample variance. Then what we are saying here is that m plus n minus 2 s p square by sigma square follows chi square distribution on m plus n minus 2 degrees of freedom. Now, let us consider this quantity and this quantity. This is z and this is say w. Then z and w, they are also independent, because x bar y bar are independent of s 1 square s 2 square, and therefore, this z and w are independent. Now, z is normal 0 1 and this is chi square. So, we can write z divided by root w by m plus n minus 2. This will follow t distribution on m plus n minus 2 degrees of freedom. Now, this quantity is nothing but, let me call it t star, this z by square root w m plus n minus 2. This turns out to be root m n by m plus n x bar minus y bar minus eta divided by s p. So, this follows t distribution on m plus n minus 2 degrees of freedom. So, if we consider here the density function of t distribution on m plus n minus 2 degrees of freedom, and let us take this point as minus t alpha by 2 m plus n minus 2 and this point as t alpha by 2 m plus n minus 2, then this intermediate probability is 1 minus alpha. So, we get probability of minus t alpha by 2 m plus n minus 2 less than or equal to t star less than or equal to t alpha by 2 m plus n minus 2, that is equal to 1 minus alpha. This is equivalent to, after simplification, probability of x bar minus y bar minus root m n by m plus n s p into t alpha by 2 m plus n minus 2 less than or equal to mu 1 minus mu 2 less than or equal to x bar minus y bar plus root m n by m plus n t alpha by 2 m plus n minus 2. So, this probability is equal to 1 minus alpha. So, when sigma 1 square sigma 2 square are unknown, but they are assumed to be equal, then the confidence interval is obtained based on the pooling of the sample variances, that is x bar minus y bar plus minus root m n by m plus n S p T alpha by 2 m plus n minus 2. This gives the confidence limits for mu 1 minus mu 2. However, when sigma 1 square and sigma 2 square are not equal and they are unknown, then the case becomes even more complicated. The reason is that this pooling which we used for the additive property of the chi-square distribution will not be possible. In the case of unequal and unknown sigma 1 square, sigma 2 square, here we will get sigma 1 square, here we will get sigma 2 square. So, when we add, we will not have a common denominator. Unfortunately, the problem of finding optimal confidence interval in this case is unresolved based on the fixed sample sizes. So, an approximate procedure is obtained using an approximate t distribution, and that is sigma 1 square is not equal to sigma 2 square. This is the case 3 and unknown. In this case, there is no shortest length, fixed width, fixed confidence coefficient, confidence interval for mu 1 minus mu 2 based on this sample. However, we have an approximate procedure. The approximate procedure is given by, it is based on, let me call it T 1 x bar minus y bar minus eta divided by square root s 1 square by m plus s 2 square by n. So, if you remember the case of sigma 1 square, sigma 2 square known, in that case we had written exactly the same statistic, but here we had written sigma 1 square and sigma 2 square, and that had normal 0 1 distribution. So, when they are unknown, we replace them by their unbiased estimators here. However, this has approximately t distribution on p degrees of freedom, where p is equal to s 1 square by m plus s 2 square by n whole square divided by s 1 to the power 4 by m square into m minus 1 plus s 2 to the power 4 by n square into n minus 1. And now, this value need not be an integer. So, we take integral part of p for the degrees of freedom. So, based on T 1, the 101 minus alpha percent confidence interval for mu 1 minus mu 2 is then obtained as x bar minus y bar minus square root s 1 square by m plus s 2 square by n t p by 2 t alpha by 2 p to x bar minus y bar plus square root s 1 square by m plus s 2 square by n t 1 t alpha by 2 p. There is yet another case where the samples themselves need not be independent. The situation may arise in the following. For example, we are considering the effect of a certain drug on patients of a say blood pressure. So, there is a medicine which those patients have been taking and it is shown to reduce the blood pressure say from the level of 160 by 120 to say 140 by 90. Similarly, a new drug is introduced, we want to know whether it will reduce further. So, now the drug is given to the same set of patients for a period of 1 month or so, and then again we observe the readings. It turns out that the blood pressure levels have gone down to 130 by say 85. Now, we want to check whether the difference is really effective. So, we want to find out a confidence interval for mu 1 minus mu 2, where mu 1 is the average reduction in the previous case and mu 2 is the average reduction in the second case. Now, in this case, even if we assume the equal variance formula, we cannot apply the test, because x bar and y bar are not independent. If they are not independent, then the formula will be invalid. However, to overcome this situation, a pairing formula is frequently utilized. Let me introduce that here. Paired observations. So, here we assume then the observations coming from a bivariate normal distribution mu 1 mu 2 sigma 1 square sigma 2 square, and here we assume that some correlation coefficient rho is there. If we consider d i's as x I minus y I, then from the property of the bivariate normal distribution, this will have mean mu 1 minus mu 2 and certain variance which we write as sigma 2 square. Now, we can consider here d bar as 1 by n sigma d I and S d square is equal to 1 by n minus 1 sigma d I minus d bar whole square. Then based on this, we can create a confidence interval d bar minus S d by root n t alpha by 2 n minus 1 to d bar plus S d by root n t alpha by 2 n minus 1. So, this is a 100 1 minus alpha % confidence interval for mu 1 minus mu 2 when the observations are paired. Let me give one example here. So, two kinds of cough medicines are there, which are given to certain patients, and we want to check their effect in having the effect on the sleep. So, for example, there are 6 patients, let me number them 1, 2, 3, 4, 5, 6. By giving the first medicine, we observe that how much sleep they are getting 4.8, 4.1, 5.8, 4.9, 5.3, 7.4. Suppose the sleep is recorded in the hours. By giving medicine 2, 3.9, 4.2, 5.0, 4.9, 5.4, 7.1. If we calculate here d bar, then d bar turns out to be 0.3 and S d turns out to be 0.45, and therefore, we can calculate the confidence interval as d bar plus minus 0.45, this is 0.3 divided by root 6, and t value, suppose I am considering say 98% confidence interval. Okay. So, we calculate t 0.01 on 5 degrees of freedom, that is 3.365. So, that is 3.365. One can get this as the confidence interval for mu 1 minus mu 2. Let me quickly also introduce the confidence interval for the comparison between the variances. confidence interval for sigma 1 square by sigma 2 square. So, we consider m minus 1 s 1 square by sigma 1 square following chi square on m minus 1 degrees of freedom, n minus 1 s 2 square by sigma 2 square following chi square n minus 1. If we consider the ratio, we get sigma 2 square by sigma 1 square s 1 square by s 2 square following chi f distribution on m minus 1 n minus 1 degrees of freedom. So, based on this f distribution points, we can construct a confidence interval for sigma 2 square by sigma 1 square or sigma 1 square by sigma 2 square. So, f 1 minus alpha by 2 m minus n minus 1 less than or equal to sigma 2 square by sigma 1 square s 1 square by s 2 square less than or equal to f alpha by 2 m minus 1 n minus 1, that is equal to 1 minus alpha. So, we get s 2 square by s 1 square f 1 minus alpha by 2 m minus 1 n minus 1 to s 2 square by s 1 square f alpha by 2 m minus 1 n minus 1 as the 101 minus alpha percent confidence interval for sigma 2 square by sigma 1 square. We can also write down the confidence interval for sigma 1 square by sigma 2 square by taking the reciprocal of this one. Today, we have discussed the confidence intervals for the parameters of 1 or 2 normal populations. In the when we are considering non-normal populations, then also we can use certain distribution theory to derive the confidence intervals. In the next lecture, we will consider the concept of testing of hypothesis.